Hey everybody, it's Mr. Carr again. Today we're going to be talking about 9B Day 1, simplifying radicals. When we talk about radicals, we are referring to this symbol right here, okay? Lots of times you've heard it called the square root. Well, a radical is just kind of the universal term because there's a radical for different types of roots. So for example, maybe I do something called the cube root. And that looks like this, okay? So a cube root is a little bit different. So today we're going to be talking about how do we handle just the square roots right now, because that deals with our quadratics a little more closely. Okay, so square root. Square root is finding a number times itself that results, finding a number times itself that results in the given number. Okay, so for example, if I take the square root of 25, what I'm saying is when I take the square root, which is this symbol right here, okay, square root, I'm saying what number times itself gives me 25. Since 25 is made up of 5 times 5, my answer is 5. Okay, a radical expression is any, oops, 1 second here. Okay, so let's try that again. Radical expression is any algebra expression that uses radical symbols. Okay, so like I said, it could be a cube root, could be a fourth root. We're going to only focus on square roots. Okay, so if, and I should have said this too, when I have a square root, it's actually assumed to be a little 2 out front. So if I write that or I write that, that's the same thing. It's only if I have to do different versions, like a cube root. Okay, for example, a cube root would be any number times itself 3 times. Okay, but we're not going to worry about those. We're just going to focus on square roots. Perfect squares. These are numbers that result in integers after taking the square root. Okay, so that is referring to a lot of these numbers here. So if I look at all of these, I'm going to go ahead and square these, and these are all examples of perfect squares. So 1 squared is 1, 2 squared is 4, 3 squared is 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, 169, I think it's 250. Oh, this is 256 here. This is 225, 196. That's what it is, right? I believe so. Yeah. Okay. These are 16, the first 16 perfect squares. They're perfect squares because if I ever take the square root of 4, the answer is 2. If I take the square root of 9, the answer is 3. Square root of 169, the answer is 13. Okay. That's what we mean by perfect squares. If I take a square root of any numbers that are not these like in between, you're going to get decimal numbers. And so they're not perfect squares then. So if your result is like this decimal number that goes on forever, that is not going to be a perfect square. So property that's going to help us today with our simplifying is, it is called the product property of square roots. For any non-negative real numbers, a and b, the square root of ab is equal to the square root of a times the square root of b. It's kind of weird, but we're saying this. If I take the square root of this number, which is a times b, I can actually separate it as the square root of a times the square root of b. Okay. So for example, if I have the square root of 4 times the square root of 4 times 9, that's the same as square root of 36, which is the same as 6. But I could also do it this way, where I split it up. I can take care of the square root of 4 and take care of the square root of 9 separately, which gives me 2 and 3. Once I multiply those together, I still get 6 as an answer. Okay, so that's just a quick way to show why this works. So let's look at some of these problems. Okay, now 52, I'm trying to think of 2 numbers that multiply to 52. The easiest 2 numbers are 4 and 13. I picked these 2 numbers because 4 is a perfect square. That's probably the fastest way to do these problems is you're looking for perfect squares when you do this. So if I separate that now, that is going to be the square root of 4 times the square root of 13. So the square root of 4 turns into 2, and the square root of 13 stays 13. There is no other numbers that, like, I can't pull out on any other squares. So that's going to stay like this. This is my simplified version. Okay. Now, if you plug these in both in a calculator, you're going to get the same answer. Okay. You're going to get the same decimal number either way. So if we take a calculator, okay, find the square root symbol. So I think those, did it pop up? No, it didn't. Okay. So find your square root symbol that looks like this and take the square root of 52 and then take 2 times the square root of 13. Should be the same thing. Okay. So we're just showing that we're kind of changing the way they look with this property. Now, there's other ways we can kind of show this because with 45, for example, I can do what's called like a factor tree. This is a different, slightly different way to do this. So I just look for any two numbers that multiply to 45. Okay. Some people look at 45 and be like, oh, that's 5 times 9. Okay. 9 is made up of 3 times 3. 5 is already the same there. When I do this, the goal here is the fact that, again, everything is still inside the radical. So because I have a pair of 3's, we're taking the square root of 5 times the square root of 3 times the square root of 3. While this is the same as taking the square root of 9. When I take the square root of 3 times, the square root of 3 times the square root of 3, that's actually going to be 3. So anytime I have a pair like this, the pair of 3's is going to turn into a single 3 on the outside. The 5 stays on the inside because it did not have a pair. Okay, so I could have done this by looking at, hey, I have a perfect square, but I can also just keep breaking it down and I look for pairs of numbers. Okay, so that's the goal with some of these examples here. 2 ways. You're either looking for those perfect squares so that it turns into something like that, or you're looking for pairs of numbers when you start splitting them up with this called a factor tree. So 121, I'm going to recognize that. I look back here, hey, that's the same as 11 squared. All right, so that's easy. Square root of 121 is just 11. Square root of 21 though. Try to think of what 2 numbers that multiply to 21. That's 3 times 7. Nothing else I can do there. Okay, sorry about that. So I was in the middle of square root of 21. When I break it down, it's 3 times 7. Neither one of those can have, neither one of them are perfect squares. I also can't break them down any further because 3 and 7 are both prime. So for simplifying, if I'm trying to simplify here, just like this right here. Oh, hold on 1 second here. That's better. Okay, so if the goal is to simplify, that means that square root of 21 is just square root of 21. That's it. That's as far as it goes. All right, so let's talk about a few more examples and then that'll be it for this one. Okay, it's a little bit tricky here. Okay, so square root of 32. Because I kind of prefer to do it as a kind of like breaking down as a factor tree, that's what I'm going to focus on as a strategy. So what multiplies to 32? It's an even number, so it's 2. So 2 times 16, that works. Okay, 2 is just going to carry down because that's a prime number. 16 is made up of, you could do 2 times 8. 8 is also something I can break down further, so I could do 2 times 4. And all those 2's carry forward. 4 breaks down to 2 times 2. So all of these carry, so I have 2 times 2 times 2 times 2 and times 2. Remember, again, the whole goal with this factor tree, we are representing everything inside the radical here. So I'm looking for pairs. I have a pair of 2's. So square root of 32 will have a single 2 on the outside for that pair. I have another pair of 2's. So this will be a 2 times 2 on the outside of the radical. This one is just a single one by itself. Okay, so that's going to be 4 radical 2. Okay, once it pops up, it stops doing that. Okay, there we go. All right, so from there, number 6 here, 54. The other, again, I'll do the other strategy again. I'm looking for the highest possible perfect squares. Well, I know that 54 is divisible by 9. So it's 9 times 6. 9 is a perfect square. 6 is not. And if I try to break 6 down even further, that's 2 times 3. Neither one of those are perfect squares either. So 9, if I take the square root of that, is going to turn into a 3. Okay, so the square root of 9 turns into a 3. The radical 6 stays in my answer. So my simplified version is 3 radical 6. Again, that's the strategy if I want to try to find, do I have perfect squares in that problem? Okay, 80 for number 7 here. If I want to do the square root of 80, again, thinking about perfect squares. Honestly, perfect squares might be a little bit difficult here, so I'm going to start doing breaking it down. Doesn't matter where I start with breaking it down. I'm going to go easy. 8 times 10 is something I see. 8 is going to be 2 times 4. 10 is 2 times 5. 4 splits up. 2 times 2. That 2 carries down. That 5 carries down. And again, I'm looking for pairs. So I have a pair of 2s and a pair of 2s. Okay, so that's going to give me a 1 2 on the outside and then a second 2 on the outside. And then radical 5 is all by itself. So that goes right there. So my answer here is 4 times the square root of 5. Okay, 121, again, that's one I don't know off the top of my head for a perfect square. So I'm just going to start with like this. That's going to be the same as 2 times, what would that be 59? Is that right? 2 times 59. No. Sorry about that. Let's see here. 2 times 60. Sorry, 2 times 60 is 120. That'll be 64. I don't know what's going on with that one. All right, 2 times 64. 64. Hey, actually, I lucked out. 64 is a perfect square. If I take the square root of 64, that's 8. Okay, so the square root of 64 is going to turn into an 8. This is still radical 2, so that stays square root of 2. Two different strategies. Find your perfect squares or break it all the way down to just prime numbers. And then you look for pairs of numbers like this here, in here. Okay, and it's any pairs of numbers. So every one of my examples here kind of had pairs of 2s. Technically speaking, if I broke this down, that would have been 3 times 3. So a pair of 3s turns into a single 3 on the outside. Okay. Anytime I don't have pairs, so for example, if I had a 2 and a 3 left over, we multiply them back together and it stays radical 6 on the inside. All right, that's it for 9B day 1. Okay, we're going to use our radicals in the next one. So we just want to make sure we're clear on this part. Bottom line is we're simplifying it, so we're turning it into these different looking radicals, but they're still equal to the same value as the original ones. All right, that's it. Take care, everybody.